Okay, here are the questions and the answers for the review. Exam 3. The first one talks about a gas-powered wheat cutter, 0.16 meter in length, and the motor rotates at 20 revolutions per second. What is the approximate linear speed? Now, the 20 revolutions per second is the linear frequency, f, and you're asked to find the linear speed. From the frequency given as 20 rotations per second, we can find the angular velocity. The angular velocity or angular frequency is 2 pi times the linear frequency, which is 2 pi times 20, that gives 120.6 radians per second. And then you find the linear velocity using this relation, omega times the radius. That was a calculation mistake. So omega is 125.6, and on multiplication you get 20 meter per second. That brings us to the second question. Here you have a wheel of radius 1 meter rotating with a constant angular speed. Now that is omega. That is 2 radians per second. What is the centripetal acceleration? Okay, now centripetal acceleration from omega. Well, the radius is given as 1 meter. Omega is given as 2 radian per second. And centripetal acceleration is also called radial acceleration. So it's AR is v squared by r, but v is r times omega. So on substitution, the r squared and the r get cancelled and you get omega squared r. So omega squared is 4, the radius is 1, and you get 4 meter per second squared. So it's important to remember that radial or centripetal acceleration is given by omega squared times r. Now the third question. Here the wheel accelerates with a constant angular acceleration. Now what's that? Alpha, 4.5 radian per second squared. Initial angular velocity, 1 radian per second. What is the angle? Which means you have to find theta. The wheel rotates through in 2 seconds. So time is given. So alpha is given. The initial angular velocity is given. Time is given, you got to find theta. So that's alpha. Initial angular velocity is omega naught. You got to find theta, and t is 2 seconds. What's the relation between these? It is theta is omega naught delta t plus 1/2 alpha delta t squared. Substitute the numbers. First term is 2, second is 9. You get 11 radians. Remember, angle is measured in radians. Number 4, the diameter is 68 centimeter, slows down uniformly from 8.40 meter per second to rest. So those are the two linear velocities, the initial linear velocity and the final, over a distance of 115 meters. Now that's the linear distance. What is the angular acceleration, which means what is alpha? So since you're given the linear velocity and you also have the radius, you have to first convert it into the angular terms. Okay, so the radius is half of 68, which is 34 centimeter, and in meters it will be 0.34 meter. Initial linear speed 8.4 meter per second. Final is 0, and delta x is the distance 115 meter. Got to find alpha. Alpha is a by r. Very important. So if we get a, we can get alpha. And we can find A using this equation from many chapters before. Rearrange that to make A the subject. And on calculation, $70.56 divided by 230, which is 0.31 meter per second squared. Since we have A, now just divide A by the radius and you get it. Well, why negative? Because it's slowing down. It's negative. Actually, it's decelerating. And you get negative 0.91 radian per second squared. There was another way to do this. You could have changed the linear velocities into angular velocity and done it. You would have got the same answer. Number 5, a 4 meter long rod is hinged at one end. So that's the pivot. And the rod is initially held in the horizontal position and then released. What is the angular acceleration as it is released? You're given the rotational inertia about one end as ml squared by 3. Okay. That's the rod and that's how it's falling. 4 meter is the length. And rotational inertia is ml squared by 3. Let's find that out first. At 5.33 m, because we do not know the mass. So in terms of the mass, and torque is Rf, and remember that the mass acts, or the mass is imagined to act through its centers, through the center of gravity. So therefore the distance of the mass from the hinge is only 2 meters. So it's 2 meters. So when you calculate the torque, that's why we are using 2 meters here, where we imagine that the entire weight is acting through. So you get 19.6 times the mass, because G is 9.8. And torque is also given by I alpha, from which we can find alpha as torque by I. Torque is 19.6 m and I is 5.33 m. So the masses cancel out and you get the angular acceleration as 3.68 radian per second squared. So we have used the two equations for torque. And in the next one, a 1.53 kilogram mass hangs on a rope wrapped around a frictionless disc pulley of mass 7.07 kilogram and radius 66 centimeter. What is the angular acceleration of the pulley? So you have this mass hanging on a rope which goes around a frictionless disc pulley. Alright, let's see what the setup looks like. That is the disc pulley, the rope going around it and the mass hanging there. The mass is 1.53 kilograms. The radius, that is the radius given, and you see that the force due to the mass is its weight, which is mg. So 1.53 times 9.8, which is 15 Newton, and then the torque is R times F. The radius is 66, which is 0.66 meters, times 15 Newton, which we got, gives us the torque as 9.9 meter Newton. Now, the rotational inertia of a disc is mr squared by 2. You got to know that. And that gives on substitution and calculation 1.54 kilogram meter squared. So we got the rotational inertia of the disc. Now let's find the rotational inertia of the mass, of this mass that's hanging down there. It's mr squared. The mass is 1.53 kilograms and it's at a distance equal to the radius. So that has a rotational inertia of 0.67 kilogram meter squared. Therefore, the total rotational inertia of the system will be the sum of the two, that is 1.54 plus 0.67, that gives 2.20 kilogram meter squared. And finally, alpha is total torque divided by the total rotational inertia, which is 9.9 divided by 2.2. So the answer is 4.5 radian per second squared. A rotating flywheel can be used to store energy. If it is required to store 1,000,000 joules of energy when rotating at 400 radian per second, what is the moment of inertia of the wheel? Okay, so now we need to remember that this has rotational kinetic energy. Need to use the formula for rotational kinetic energy. Omega is given as 400 radians per second in the proper units, and we know rotational kinetic energy is 1/2 I omega squared. Make I the subject, get 2E by omega squared, substitute and we get it 12.5 kilogram meter squared. So you see that the rotational inertia of the flywheel is really big, and that is why it can be used to store such a lot of energy, 1,000,000 joules of energy. And in this next question, a solid sphere, mass 1 kilogram and radius 0.01 meter, starts from rest and rolls without slipping down a 1 meter high inclined plane. What is the speed of the sphere when it reaches the bottom of the inclined plane? Now you got to remember that when the sphere rolls down, it has both rotational kinetic energy and translational kinetic energy. Why? Because for sure it's rotating about an axis passing through its center, and at the same time its center is moving in a straight line. So initially it has potential energy, and as it comes down, all that potential energy is changed into these two forms of kinetic energy. So that's the inclined potential energy. At the top is mgh, which should be equal to the kinetic energy at B. And as I said, kinetic energy is both rotational plus translational. A very important concept. We use the conservation of energy here. Let's calculate I first, and I for a solid sphere is 2 by 5 mr squared. That is the rotational inertia, which on substitution gives 4 times 10 to the negative 5 kilogram meter squared. I should have said kilogram meter squared. Okay, there is a meter squared there. And then when you take that, and omega is V by R, so that is why you have V squared by R squared. Again, omega is V by R, so plus 1/2 mv squared. V squared is common, taken out. And the 2 on the right hand side, you see the 1/2 on both terms, that's taken to the other side, becomes 2, or in fact we're substituting, multiplying each term by 2. So that is 2 mgh. I is 4 times 10 to the negative 5. The square of the radius is 10 to the negative 4, plus the mass is 1 kilogram. So we get V squared is this, and then take the square root, to find the velocity as 3.74 meter per second. In the ninth question, there is a hoop of radius 0.5 meter and a mass of 0.2 kilogram. It's released from rest and allowed to roll down an inclined plane. So this is a question that is similar to the last one. But the only difference here is that it's a hoop instead of a solid sphere. It's like a ring. And how fast is it moving after dropping a vertical distance of 3 meters? Exactly the same. First, we have to find the rotational inertia of a ring, which is hoop, is given by mr squared. And once you get the rotational inertia, apply the conservation of energy as before. The potential energy at the top is equal to the sum of the rotational kinetic energy and the translational kinetic energy. Again, multiply all terms by 2 and substitute for omega as V by R. And we're trying to separate out the velocity because that's what we have to find. So that's the equation we get for V squared. It's a good idea to substitute the numbers at the end, so you don't have to write it many times. That's 2 mgh. I is 0.05 by square of the radius is 0.25 plus the mass is 0.2 kilogram. That gives 11.6 by 0.4. That's 29.4. Take the square root of that and you get 5.42 meter per second. In the next one, moving on to the next chapter, what is the radius of a sphere that has a density of 5,000 kilogram per meter cube and a mass of 6 kilogram? You can already see the answer because it's direct. Density is mass by volume, and the volume of a sphere is 4 by 3 pi r cube. Rearrange that to make rho the subject after you substitute. In fact, make the radius the subject. You get r cube is 3m by 4 pi rho. Substitute the numbers, get r cube and then take the cube root to get the answer as 6.59 centimeter. In the next question, the object's angular momentum changes from 20, changes by 20. So that's the change in angular momentum and the time. You got to find the average torque. Average torque is given by change in angular momentum divided by time. Delta L by delta T, change in angular momentum is 20 and the change in time is 4. So you get the torque as 5 meter Newton. Remember, it's the same as writing it this way. Torque is delta L, which is change in angular momentum by time. And then 12th question. A lever is 5 meter long. The distance from the fulcrum to the weight to be lifted is 1 meter. If a worker pushes on the opposite end with 400, what is the maximum weight that can be lifted? Let's get a diagram. That's the lever, 5 meter long, but from the fulcrum to the weight is 1 meter, as you can see. The worker pushes down there, applies the force F. So when you take the torque about the fulcrum, you see that F times 400 times 4 should be equal to W times 1. Clockwise, total clockwise torque is equal to total counterclockwise torque, and you get it as 1600 newtons is the maximum weight that can be lifted. Now here the F creates the counterclockwise torque while the weight creates the clockwise torque, and You have to have the perspective of where the fulcrum is. That's why this is trying to rotate it this way, counterclockwise, and this is clockwise, because the fulcrum is here. All right. That brings us to the next question. It's a uniform board of weight 40 newtons supporting two children weighing 500 newton and 350 newtons respectively. The support is at the center of the board and the 500 newton child is 1.5 meter from the center. What is the position of the 350 newton child? Here the important thing is to understand that although the board has a weight, because you can imagine that the weight is acting right through its center and that is where the support is, its weight does not create a torque because there is no distance. The weight of the board does not create a torque. So that's the board, that's the child seated, 500 newton and 1.5 meter away. That's going to create the counterclockwise torque, and the other child, 350 newton, and we do not know the distance, so let's say x. That's going to create the clockwise torque. The weight of the board need not be considered because it does not contribute to the torque. And for equilibrium, the two torques have to be equal. Put them equal to each other, calculated. And the other child has to be seated 2.14 meters away. 14. A 500 newton force, a person stands on a uniform board of weight 100 newton and length 8 meter. The board is supported at each end. Now there are two supports. And if the support force at the right end is 3 times that at the left end, how far from the right end is the person? In this case, we have to use both the conditions for equilibrium. Number 1, the total upward force should be equal to the total downward force. Number 2, if you take the torques about a particular point, the total clockwise should be equal to the total counterclockwise. Now let's get a diagram first. That's the board. So those are the two supports and those are the reactions there, support force, and we call them F1 and F2. And this 500 newton person is standing there and the weight of this one acting right through its center, the weight of the board, because it's a uniform board, its weight acts right through its center is 100 newton. Therefore, the first condition, the total upward force, F1 plus F2 is equal to the total downward, is equal to 600. But the problem says that F2 is 3 times F1. So, we can get F1 now. 600 divided by 4, which is 150 newtons. Now the second condition. We're going to take the torque about one end. Why? Because if you take it about one end, it automatically cancels out the torque. Okay, the right end. So now there's not going to be any torque due to F2 because there's no distance. And then because we're taking the torque here, 500 and 100 both are trying to rotate it this way, which is counterclockwise. But this force, F1, is trying to rotate it clockwise. That's because we're taking the torque at this point. Okay. Now that distance, we do not know. We have to find that. That's x. So 500 times x plus 100 times the distance, which is half of the length of the board, which is 4, should be equal to F1 times 8. F1 is 150. Therefore, okay, those are the directions of the torques now, and we're taking the pivot there. Yeah, the arrows show clearly which ones are clockwise and counterclockwise. So now that is simple math there. 1200 minus 400 is 800, and then divided. 800 divided by 500 gives 1.6 meters. In the next question, a brick weighs 50 Newton and measures 30 by 10 by 4, all in centimeters. What's the maximum pressure it can exert on a horizontal surface? Pressure is force divided by area. Since the problem says maximum pressure and the force is just 50 newtons, and you want the maximum pressure, so the brick must be placed on its side which has minimum area. You see how that works? Because when the area becomes smaller, the pressure becomes bigger. So which would be the minimum area side? Of course it will be 10 times 4. So that's where the area is. Okay. So pressure is maximum when the area is minimum. Okay, that's the point in this question. Pressure is force by area, force is 50 newtons, and the minimum area is, now both are in centimeters. 10 times 4 is 40 centimeters squared. Got to change it into meters squared. What do? Divide by 100 times 100, which will be 10 to the negative 4 meters squared. Now just divide the force by the area. 50 divided by 40 times 10 to the negative 4. And that gives 1.25 times 10 to the 4 pascals. Or 12.5 times 10 to the 3 pascals, which is 12.5 kilopascals. Yes. This question was on the quiz, but again, a circular window of 30 centimeter diameter in a submarine can withstand a maximum force of 5.20 times 10 to the 5 newtons. What is the maximum depth in a lake to which the submarine can go without damaging the window? Pressure due to liquids is H rho G. Here the forces are given, and the area, we got to find the area of this circular window. There is pi r squared, that's the area of a circle. The radius is 15 centimeters, which is 0.15 meter. Gives 0.07 meter squared. So when you divide that, you get this pressure. That's the maximum pressure that can act. And now we say, alright, pressure by the liquid is H rho G. So H is pressure by rho G. Rho is the density. You got the pressure. Density of seawater is 1025. It will be given to you. And G is 9.8. Okay, I'd forgotten to put the 10 to the 5. Now I'm putting it on. It's 10 to the 5, and another mistake that I was making was, sorry for that. It says it's a lake. If it's a lake, it's not salt water, it's just fresh water. So the density is 1000. And therefore you get 750 meters. I almost missed that. Okay. And in the next one, we have a hydraulic machine, those machines where you apply a small force on one side and the liquid transmits the pressure equally to the other side, and therefore you get a bigger force. The kind of machines that we use in service stations to lift huge automobiles, that's what we're talking about. So here there's a 500 Newton weight sitting on the small piston, which has an area 2 centimeters squared. The large piston has an area 40. How much weight can it lift? Pressures are equal on both sides. Pressure is force by area. So the bigger force by the bigger area should be equal to the smaller force by the smaller area. Rearrange. Small force is 500 newtons. The bigger area is 40. We can have it in centimeters squared here because it's a ratio and it'll cancel out. So you get 500 times 20, which is 10,000 newtons. So see that a 500 Newton force is converted into a 10,000 Newton force. 22. This again was on, I think, a quiz. A 4 kilogram cylinder of solid iron is supported by a string while submerged in water. What is the tension in the string? Remember that in the string you have three forces. One is the tension, the other is the weight, and the third is the buoyant force. And tension must be equal to the weight minus the buoyant force. Why? Because weight is acting down and the buoyant force is acting up. And buoyant force is given by weight of fluid displaced, which is volume times density times G. And the volume in this case is the volume of the iron, which is its mass divided by density. The mass of the iron is 4 kilograms. And its density, which will be given, it's given, but what's given is a specific gravity or relative density. You got it multiplied by 1000 to get the density in kilogram per meter cube. So that's why it's 7860, and that gives the volume, which is the volume of the iron, exactly the volume of fluid displaced because it's completely submerged. I hope you're getting this. Therefore, put that volume times the density of the fluid now, which is water. It's 1000 times G. You get 4.98 newtons. So therefore, the tension is the weight is mg, minus the buoyant force, and you get 34.22 newtons. A rectangular box of negligible mass measures 5 meter long, 1 meter wide, and 0.5 meter high. How many kilograms of mass can be loaded onto the box before it sinks in a lake? Interesting question. Because the maximum volume that this box can displace is equal to its volume. And its volume is 5 times 1 times 0.5. And so we have to find out the weight, the mass of the liquid displaced. Let's do it. The first thing, that's the volume of the box. As I mentioned, is length times width times height. That is 2.5 meter cube. Now, the weight of fluid displaced, that's the buoyant force, is Vf times rho f times G. The F there stands for fluid. So that's equal to 2.5 times the density of water times 9.8. $24,500 newtons. Therefore, the mass of fluid displaced is just... Now, remember that if it should float, the mass of the floating object should be equal to the mass of liquid displaced. Or the weight of the floating object is equal to the weight of liquid displaced. That's the weight of the floating object, which is that's actually the weight of the floating object. So I need to tell you that this is the weight of the floating object, and to get the mass you have to divide it by 9.8. Okay. A polar bear, mass 200 kilograms, stands on an ice floe 100 centimeters thick. What's the minimum area of the floe that will just support the bear in salt water of specific gravity 1.03? Specific gravity of ice is 0.98. Interesting Again, interesting question. Let me just draw the ice floe first. It has a certain thickness which is given, and you have to find the area. The weight, the total weight, I must say the total mass is 200 times the mass of ice. Okay, weight of ice is Vi times rho I times G. Volume is area times thickness, and the area is unknown, which is what we're trying to find. So A times 100 centimeter is 1 meter. That's why you find A times 1 times 980 times 9.8. So that is the weight of the ice in terms of A. Okay, see, I had forgotten to multiply it by 9.8. Now I've done that, plus 9604A. That's the total weight of the floating object. And the weight of fluid displaced is Vf times rho F times G. And the volume of fluid displaced would be exactly the total volume of the ice floe, which is A times 1. But the density of the fluid is 1030. Okay. Because the specific gravity has to be multiplied by 1000. Okay. So now you get the weight of the fluid. Now put them equal. Because to float, the weight of the floating object should be equal to the weight of fluid displaced. And bring the terms that have the A onto one side. So that makes it negative 9604A on the other side. Take the difference between those two. And then A is equal to 1960 divided by 490. On dividing it, you get 4 meters squared. So that's the minimum. Oh, now that's the polar bear that has come down. Okay, so that's 4 meters squared. Okay, in this question, the torque is given, and you have to find the mass of the disk. So first, find the rotational inertia using I is tau by alpha. Torque is 12. Angular acceleration is 5.7, so you get 2.10. But again, for a disk, rotational inertia is mr squared by 2, from which make the mass the subject. We already know I from here, so substitute that and you get it as 16.84 kilogram. And I sincerely hope that you will spend some time to go through all these questions, and because many of these questions will be on the exam. Thank you and good luck.